We then move to composite bodies, where break it into parts that you know the location of the centroids are. We move from integration to summation. Continue to think about those moment arms. If you're struggling with it, go back to uniform density, uniform gravitational field, and you have these little force vectors coming down, and you have moment arm, the distance away from that axis. You exploit symmetry, and you want to get good at that, looking at an object. And if you do have a continuous system, but then there's something missing, they put a hole in it, you can actually do it with a composite body treatment where you have a negative volume or negative area or a negative length, treating it as if it's there and put a negative in. And use table to help organize the calculations. I'll try and demonstrate it. It says locate the centroid of the beam cross-sectional area. Hopefully that looks like a beam. Okay. Is there any symmetry that we can exploit for this? Yes or no? I see a head shake. Yes. Yes. All right. Is it symmetrical about the x-axis? Or is it symmetrical about the y-axis? About the y-axis. So where is, this is a tough question. It's a clicker question. So do we conclude from symmetry that y bar is equal to 0? Answer A. Or that x bar is equal to 0? Answer B. Or none of them are true? Answer C. So I can look at the results and I know I don't have 100% correct. So what I'm going to do is I'm going to ask another question. Okay, I'm going to ask the question this. I'm going to say, somebody says that this is the location of the centroid of that cross-sectional area beam. And another person says, no, it's not there. That's way too low. This is the location of the centroid of the cross-sectional area. Which one do you think it is? Not a clicker question, but A or B? Can somebody volunteer and just call it out? Which one? A. It's closer to A, right? All right. Somebody says, well, I think maybe A is that. You're right. I agree, but I think it's closer to this edge. I think it's A or B. Somebody else other than you. Which one is the centroid visually? A. You're still staying with A, right? But okay, somebody says this one, this. They've got something correct here, don't they? If they say it's here or here or here or here. What do these all have? Do these, all four of these that I've shown here, do they all have the same Y bar or the same X bar? Let me ask that question, clicker question. All four of these, the first one, second one, third one, fourth one, those are my guesses at the location of centroid. Did they have the same X bar? Answer A. Or the same Y bar? Answer B. All right. Let me ask this. Somebody, this problem has where's the location of the origin? If this is the x-axis moving positive out, this is the y-axis moving. Is this the location of the origin for this problem? That looks good. What is the location of this point right here? Is it 3 centimeters, 0 in the y? Is that true? Okay. How about this point right there? Is it 0 in the x, 6 in the y? All right. What is this location of that point? Is it 0 in the x and 27 plus 6? What is that? 33 in the y? How about go way out here? And this is a tough one, right? What is the location of that point? 12 in the x and 36 in the y? Did I do that okay? I don't know why I'm not getting 100% correct on that question. Basically, the x bars are all 0. The location of the centroid with respect to x is along that. And so I should have had 100% correct, I thought. But let's go back and now grade this one. And so what did we ask? We said the locate the centroid of the beam cross-sectional area. Is y bar equal to 0? No. Isn't it? Isn't x bar equal to 0 from symmetry? All right. Hopefully more of you got that. So part of the answer is x bar is equal to 0. You could put in there centimeters, but it really doesn't need units because it is 0. Done for that part. Now how to calculate that y bar. Okay, how do I calculate this y bar? You can do it so many different ways, it's almost not funny. But I would observe that, oh, this looks like the composite of 2, 3, or 4 bodies that are easily determined. So I would look at this one and I'd say, first of all, it's symmetrical. I'm only going to have to do half of the problem. And I'm really only interested in calculating the y. I'm going to call this part 1, this part 2, and this part 3. And I'm going to organize it in a table. So it's the number of the item. Here it's the number of the area. We have 3 areas, area 1, area 2, area 3. Okay. Then I say, what is the total area of each of those? And the units are centimeters squared. So what is the area of 1? 6 by 6? 36? Is that right? Is it 36 centimeters squared for 1? Well, I'm not going to go all the way over here. I can do just half. But if you're right, if you're going to do the whole thing, you'll get the right answer. You'll just have everything. Okay, how about this one? What is the area of 2? 27 times 3, right? So let me move here. That's 81. And what is the area of the third? 36. Very good. Now, if we want to calculate the y bar of the entire system, I have to observe what is the y bar of each piece. And that's in units of centimeters. So with respect to the same coordinate system, what is the location of that centroid? What is the y bar for 1? 3. All right, then I come on here and I focus. What's the y bar of 2? Is that going to be 6 plus 27 divided by 2? Does that give us the right answer? Sure, and then that turns out to be 19.5. And then what is the y bar of the third? Way up here. That location is 6 plus 27 plus 3 divided by 2. And somebody already called it out, 34.5. True? Now we make the product of y bar for that each entity times the area of each entity. Maybe I put I there. You could put I subscripts on all this, but you know it's on that line, it's for that entity. And so it's going to be 36 times, it's 1242, and then it's 1579.5, and then it's 108. What do I do with that column? I add it up. If you ever see that notation in your statistics class or even math classes, that summation for that column, it comes in at 29.5. What are the units on that? Well, it's centimeters cubed. Centimeters cubed. If we sum the area, that comes in at 153. We have the two things to give us the ratio, so that y bar is equal to the sum of yi times the areas for each of those, and then divided by the sum of the areas. So here it's the 29.5 centimeter cubed divided by 153 centimeters squared, and y bar comes in at 19.15 centimeters. We should check it. We should try to figure out, okay, where is that at? If you look at it, This was a 19.5, so it's a skosh below, just a little bit below the centroid for the second area, for the Y bar. Make sense? Very good. All right. I want to solve this problem. Locate the centroid of the bracket that is made of a uniform thickness sheet metal that's been bent into an L shape. So the sheet metal is a plate, and then they bent it, and then they popped 4 holes. 1, 2, 3, 4 holes. Those holes have 10 millimeter diameter. So this is a composite, so we'll tabulate to calculate the centroid. So which of these we're going to calculate? X bar, Y bar, and Z bar. True? X bar, Y bar, and Z bar. Question, is there any symmetry that we can exploit for this system? If there is, answer A for yes there is. Or you say, no, I looked at it, I don't see any symmetry, no symmetry for this problem. Is there any symmetry we can exploit for this problem? Yes, there is symmetry, isn't there? And it's symmetrical about which plane? The XZ plane, isn't it? If I cut it, the XZ plane, it goes to the origin. And I flip it back and forth, it's symmetrical. So with that, I'll ask the question, is either X bar equal to 0, answer A, or Y bar equal to 0 because of symmetry, answer B, or Z bar equal to 0 because of symmetry, answer C. All right. Well, we're not 100% correct on this, but we're pretty close. We were asking to find that location of the centroid, and the centroid, because it's in symmetry, is going to be somewhere in this XZ plane that goes through the origin. It has to be on that plane because of symmetry. So basically B is the correct answer, isn't it? All right. Okay. Now that we have exploited symmetry and we now have 1/3 of the question answered, let's go and try to answer for the other, X bar and Z bar. Well, we would make a table and we would say, how many entities do I have? You can count them up. I can go the long way, the short way. Some people will be different. Here, I would put table entity 1, entity 2. What is entity 1? It's like this. Well, why didn't you combine them and just call it entity whatever? You could do that, no problem. Okay, this would be 2. This would be maybe 3. This would be 4. All right, and then I have the holes. So let's call hole 5, hole 6, hole 7, and hole 8. Somebody says, oh, I can simplify and reduce the number. I know you can, that's fine. But this'll work. Okay. All right. So we'll have 1, 2, 3, 4, 5, 6, 7, and 8 entities. What would probably be the first one in there? Wouldn't it be like maybe the area? And so what is that? Area in units of millimeter squared. And so for 1, what is it? 60 times 60? That's 3600. How about for 2? Well, that's 3600. How about for 3? 3600. 4, 3600. Like I said, you could have combined and just had 2 of those, but that's okay. Then we have hole. All right. What is the area of the hole of diameter 10 millimeter? Is the area of the hole pi r squared or pi d squared over 4? Because they give us a diameter. Pi r squared is the area, or pi d squared over 4? Look good? And so we would put in here the 78.54 millimeters squared. At this point, we put a negative because it's not there, and we just treat it like every other area, and it'll make the math work. 78.54, negative 78.54, negative 78.54. Okay. Now, if we're interested in calculating an x bar, I'm going to get x for each of those entities. So what is the x bar location in millimeter for 1? Can you see what that is? The centroid of 1, that's easy to determine. Oh, it's right there. What is the x bar for 1? 30. All right. How about the x bar for 2? 30. How about the x bar of 3? That's a little harder, right? X bar of 3? Is it 0? Good. And then 0. Now, what is x bar of the whole? The fifth 5, the first whole. 0, 0, 0, 0. It's almost too easy. But the table helps organize. Now, what we do is make an additional column, the product of x times a. For the x times a, you get 108,000. Those are millimeter cubed. And you get 108,000. The rest of them are zeros. I mean, these are all zeros. You sum that column, you get 216,000. You sum for the areas, 16,486. I take the ratio of those two to calculate x bar. And I'm going to do this. I'm going to ask you to calculate it and give it to me alphanumeric in 3 significant digits in units of millimeter. All right, let's just go ahead and show the results. So it's 13.1. One of the things that you can do whenever you're calculating x bar is kind of look at it. Would it be lower than 0? No. Would it be greater than 60? No. Right? It doesn't look reasonable. It's about 13. It's right in here. Right in there for x bar. X bar is located somewhere like 13.1. All right. So we calculated 13.1. How do we calculate z bar? Well, you make an additional column z times a. There's some more. Whoops, I got to get z first. What is z for area 1? What is the centroidal location z? It's 0, right. How about for 2? 0. How about for 3? Well, you're going up how much? The total is 20 plus 40 plus 20. That's 80 up. So halfway up is where the centroid is. Isn't that 40? And then what about for the next one? 40? All right. How about for the whole? What is the z bar for the whole 5? 20. Yeah, 20. Don't put a negative sign on that. Just like we already had the negative sign for the size of it, the area or the volume. All right, then it's also 20 for 6, and then for 7 and 8, they have the same. It's 60 and 60, isn't it? And then z times a, you make that additional product. Let me just fill it out. So we're going to have 192,000. 192,000, negative 1,571, negative 1,571, negative 4,712, negative 4,712. Then we add up that column. We get 371, 434. Now I ask the last quicker question maybe for the day. Give me z bar. 3 significant digits. Well, then you would have had it too. So 22.5. And then again, I encourage you when you calculate a number like that, kind of look at it, you know, say, is that reasonable? Why isn't it closer to, what would that be, 40? Well, because there's a whole lot of sheet metal at Z equal to 0. So that brings it down. So it's 22.5 millimeter. So those are the answers. All right. Any comments? Ready to press forward?